change a little bit and tell you all that my first computer was a 286 IBM. That should put a little perspective on the gentleman with vast experience. So if I fumble through a little bit on the experience here, cut me a break. So I've been working with at Oak Ridge National Lab for about 2.5 years in the user assistance team. Our role there is to help users whatever they need, whatever it takes. So if one day you become a user at OLCF, I might be one of the people to help you. We have a huge team, and I'll talk to you a little bit about our team. So I'll do a little bit of an overview of our center. I'm going to try to prove to you that there's no return and Many4 is here to stay and assimilate where else. I'm going to talk a little bit about how we helped users transition from Titan from Jaguar, and then I'm going to tell you all the lessons learned and how we see the coding for the future and what it's going to look like. So that's my future prediction. But remember, I started on a 286, so perspective, I'm lacking a little bit of perspective. So LCF Services, we have a variety of services, or people, just in terms of people there. I'm in this second column here, user assistance, so we help anywhere with software tools. It can be anywhere from I can't log in, I've logged myself out, to my code won't scale, what's wrong, and we try to help users with that. There's a whole other number of about 30-some people. They're called liaisons, and they help specifically with one of our allocation programs called Insight. And they're one-on-one with these projects, sometimes 1 to 2 projects. We have a whole biz team. Actually, we're hiring biz, so if you know somebody that can do biz and would like to do cool biz, please let us know. We have a huge wall. That'd be cool too. So if you have visualization you'd like to do, it's 3-dimensional. You can put these super goggles on with little balls, and it'll track you where you are. It's pretty cool. If you like to just come and tour and see it, you can do that too. And then there's outreach. You know, we try to educate everyone on the science being done, and Jack's a big part of that. And some of us kind of try to sprinkle it around, and we write articles and we talk about the science being done in our center, and that's ultimately how we pay our bills. So open science is how we can stay open. We've grown in leadership computing capacity over the years, 10,000-fold. Titan is the latest iteration of that. It started in 2004. I won't go too much into the history, but we've been around for 10 years. You already saw this from Jack. It's not getting any better, and the one that I like to use is actually this one. This is per core performance. The per core performance is going down, but the number of cores subsequently has to go up because, well, you like to keep flops, right? The one I really like too is this one, the watts per square centimeter. And you notice that we're just below the line of nuclear reactor. So there's no way we're crossing the line, and I hope this slide, if nothing else convinces you that many core is the way of the future, we're not going into nuclear reactor watts per square centimeter. So, all right, so I've convinced you now, you're all been assimilated. That accelerators in whatever form they look like, these are the current forms. I know the form factors are going to change a little bit in the next few years, but currently that's what they look like. So it's an offload mode. And that's what we went with on Titan. And I'm not going to reiterate that. This is just here for completeness for somebody that gets these slides and goes, where is she going? She's everywhere. So I'll just leave this for completeness, but you know that Titan was the way we chose to go. So teaching people how to use, now back to training and putting on my training hat. So my role at User Assistance is to read the tickets, see where people are having trouble, and then try to come up with training scenarios and training circumstances to address it. And with Titan, I had just come on board. So before Titan was online, Titan came online about January, December 2012. I came on board about March. The whole concept of offloading computation to the GPU was foreign to a lot of folks. And so that was a huge transition. It was a very major transition for a lot of people that have been kind of used to, you know, large memory growing and just buying new hardware that just sped up their code. That shift was really, really hard because it's hard to expose that extra parallelism, right? And we've been talking about this all. But also hard because data locality is really, really important. And John mentioned that. And others have mentioned it in various other ways, but data locality is really what's killing all of us trying to migrate to accelerators. So a little history. These are my little drawings, and I like them because I made them. So a little history. I do remember the days of single core. I was an undergrad that didn't know much, but I was tasked to write my first program in high energy physics, and I didn't know anything about programming at the time, but I learned, and it was Fortran because that's the only true language that matters. And I started with, and there were single cores, and it was a Beowulf cluster, and I figured it out. I figured out how to put this thing together, and I was running these simulations, and at the time there weren't even MPI. I would just kind of send these tasks out to other Beowulf little clusters, and I'd run these things. So it was really sophisticated for me at the time. But it was a single core. I didn't have to worry about much. And then later on, I integrated MPI, and I did a better job at the little program. And then I left because I thought I sucked at computing, and I ended up going to service physics. But that's another story for another day. But later, when I came back to computing, there was many cores. There was multi-core. So the CPUs now had cores, and simple, just put MPI on cores, right? That's what happened. It's not, and I wasn't the only one. Everyone else did it that way. No one really tried to do a really sort of threaded way. They just kind of said, okay, I have more CPUs, therefore I use more MPI RAM. Okay, well now these codes are now 10 years old, 15 years old, right? And then OpenMP comes around and builds up a user base, but a lot of codes got left behind. They did not add OpenMP threading. Some added p-threads, many added OpenMP, but a lot of the legacy physics stuff stayed in more CPUs, more cores, more MPI rings. So now that's what we have. What we have coming into our center looks like that. More MPI rings. That's what we had in Jaguar. 16 cores, more MPI rings. Not a lot of OpenMP. So that idea of threading is actually very new to a lot of folks that are a little bit younger than me. The idea of adding extra threading to their code. In fact, when I was going to grad school, the computer programming course at the time was C++ still. And right after me, it changed to Java. And nobody cared about memory anymore. Because, Java manages it for you. So there's a whole slew of people that are just slightly younger than me that, who cares? It just manages it, right? I forgot to deallocate, so what? What happens to it? Well, it ran out of memory. That's why it crashed. So now we're looking at directives. OpenMP's, listen, threading is here to stay. We need to use more threading, whether it's hardware threading or whether it's software threading. Threading is here to stay. Directives, I think, are probably the easiest barrier to get started. We've seen how you can get penalized right away. You can see that things, when you just put in naive implementations of directives, your code can slow down, yes. But again, data. That goes back to data, right? Data locality. So I've been trying to focus our training on, okay, directives, threading, data locality. It's been my concentration for the last year and a half now. And it's been okay because, well, with threading, there's one accelerator, and using directives with one accelerator actually works pretty well, unless you're one of those folks that have the MPI and it just increased MPI ranks, and I need to use a little proxy software in the middle of that to kind of manage those different processes. But so long as it's within one process, things work really well, and you can use an accelerator. But what happens when, who was it that said that they had 16 GPUs on one node? Somebody said that here. What happens when you have more GPUs per node? More accelerators. What happens when your accelerators are everywhere, or there are APUs that are built on maybe the same silicon? What happens then? Well, things are going to get more complicated, and what are we going to do with all of that? I don't know that I can tell you an answer, so whoever started that answer, I hope I can answer some of that answer some of that question as we go along, but the question earlier was, well, what do I do? Who's you that asking? Which one do I choose? And the cop-out answer I'm going to give you is, the best I can give you is, it depends. And maybe, and I'm going to tell you why it depends. But this is where we are. This is the next step iteration, right? This is where we see the next step iteration is, we see multiple devices talking to multiple, or it's single host or multiple hosts, or we see multiple devices in different layers and levels of threading within those devices. So like, Phi might have hardware threads within a specific core. So we see these different levels of acceleration. So that means, and then don't forget I/O. Constantly the tickets that come in for us is now you have more MPI rings, or you have more accelerators, and you have more data, and now what do? And I/O data placement. So hopefully I'm painting a picture here. We have different kinds of cores, right? So far the picture is we have different kinds of cores that do different things well, and we have data placement is an issue. Whether it's all the way to the file system, all the way down to the core. So the path to exascale is hierarchical parallelism, right? Explicit data management, and data locality is very important, and expose more parallelism. Those are the sort of the 4 pillars of things you need to concentrate on if you want to prepare your software, your application for the future. Those 4 things, and John mentioned those things in his talk. First you start with flops, then you start with data, then you go back to flops, then you go back to data, and you keep doing that back and forth. How many times do you do that back and forth?
You can never stop.
That's right. You can never stop. So heterogeneous multi-core processor, use the right processor for the right task, and then be aware of where you're placing your data. So, back to your question. Applications, libraries, OpenSCC, OpenMP, directives, programming languages. Well, that depends. And this is one of the slides that I stole from NVIDIA. So whoever you are, but I changed the last thing here, and what I changed it to is Max. I forgot what it was, but I didn't feel like it fit. So maybe you guys want to correct it. I don't know.
I changed it from performance.
You changed it from performance? Well, we have to talk about that because I felt like performance really fit in that area. And we can talk about you can I don't know, harass me after question during questions. But I felt like really what you really want is you want something that's drop in, but may not be ready. You know, libraries are not always they're big things, they're behemoths, and new architectures come along, and is it going to be ready right away? And if time is of the essence for you, maybe libraries may not be what you want to consider. Libraries are certainly easy, and I always recommend libraries first. Number 2 is you can use the directives. If you have something that you have control over, especially if you have control over your source code, try that. It's a very low bar, right? 10 minutes, you can get that right away, and it will slow down your code, and then you're going to have to spend more minutes optimizing it. But in 10 minutes, you can get something. And then it's, and then you can give us feedback, and I'll tell you a little bit how you can give us feedback, and how we can improve that. And then the last one, programming language. So, closer to the metal, the closer to the metal you get, you probably have a lot more control on what you're doing with your data placement. Having a lot more control what you're doing with your flops calculations. And hopefully, if you know what you're doing, and you've been around for a gazillion years, you can do that right away in 10 minutes. And the reality is, it would take me a lot longer than 10 minutes, and I'd probably not get very good performance compared to, say, something like a directive approach. But performance, if performance is your thing and you're really good at it, go for that. So it depends on what it is that your short and long-term goals are. So what we learned from Titan and transferring some of the applications from Jaguar to Titan is it takes about 1 to 2 person years required to port each of the codes that we had on the car effort. About 70 to 80% of the time was just code refactoring, just moving data structures, just rearranging the code because we got a little lazy. Let's admit it. We got a little lazy over the years. We just buy a computer and things got instant improvement. But what's good about this is that those sorts of things that we didn't learn back in school because we were taking Java instead of C++ and optimization, is that those things kind of carry on for a very long time. These are lessons that folks that had computer science back in the 80s had learned, and some of us younger ones that had computer science in the 90s kind of got cheated on in school. But then each team must make its own choice. And it depends, for a lot of our users, a lot of our users are scientists. They're not there because they got computer science degrees. Some teams have a combination of computer scientists and scientists. I was talking to somebody here from Total, I was talking to the two gentlemen from Total, and he was telling me exactly that. His team is geophysicists, computer scientists, HPCers, and hardware people. I mean, your team is a mishmash of people. So it depends on what your skill sets are in your team. It also depends on your code base. How large is your code base? Lines of code was a huge issue for some of the codes that we were reporting. They had anywhere from 500,000 lines of code all the way down to, I think, the smallest one was something like 80,000. Is that correct? Somebody remember, Jack? Do you remember? One of the smallest lines of code? It doesn't matter. But a lot of this depends. But we're hoping, too, that funding agencies, and if funding agencies are private or public, if you're a company, tell them that investing in software, this is how you make your bread and butter. Investing on software development is very, very important. And that's something I think more and more people are realizing. So a few lessons from CAR. Prepare applications for, the objective was to prepare applications for accelerated architectures. We selected 6 of them, and the repeated themes were finding more threadable work, improving memory access patterns. Every single one of these applications suffered from this or had to work on this. Making GPU do more work, more coarse-grained if possible, making data on the GPU more persistent, stop that transfer, right? The PCI bus on Titan really kills folks. Because in fact, on XK7, it's a PCI 2 bus, so it's a lot slower than the XC3. Overlapping data transfer, that asynchronous kernel data transfer, and as much as, same thing as I said, use as much asynchronicity as possible. The difficulty level for the GPU port, structure of the algorithms, some algorithms are really, really hard, especially for communities that have been around for a long time. Some codes have been around since the 80s, and those are really, really difficult to restructure without making some major changes. So for climate, for example, it requires a lot of revalidation of the code to make sure that it gets used by the community. And that's very burdensome for them. So they like to keep the code structure as intact as possible. This is where directives have the advantage. Lines of code. We're talking about lines of code. 30x thread parallelism may be needed for exascale. So now we're getting into the topic of exascale. I mean, this is the path that we are going as a leadership computing facility and other facilities that offer these sorts of computers where you can't get this kind of computing power anywhere else. So we're marching right ahead to exascale, just like we march right ahead to petascale and terascale and all that. So we're thinking 10 years down the line, right? These machines only last between 4 to 5 years, and your code, your applications last a lot longer than that. So what you do today and how you change it today will determine whether or not it can run in 2 generations from now, 3 generations from now. So what is it going to look like? Well, we can do that MPIX. John talked about that, right? Keep doing the same thing you've been doing for 25 years, just do it in an innovative way. Well, we can continue with MPIX, yes. What X is, it depends. And it depends on what you want right now, and I don't think there's anything that's really kind of settled yet on what the direct path and the easiest path. Until accelerators, I think MPI and OpenMP, or MPI and P-threads was just fine. Or more MPI rings. You had 3, and now we don't have 3 anymore. We have all of these other things that have come online. And it's getting more and more difficult to choose. But we're here to help. We're the government, we're here to help is my favorite line. And so how I can help with that is, if we don't have oil and gas, for example, in our user pool, I don't understand what needs you might have for training. And so one of the questions I had to the folks at Total, I was sitting at lunch, was, what do you think we need to do to help you guys move on so when the exascale is here, you're ready. You're ready to go. So what is it that I need to do? And part of that requirements gathering for me comes from the users that use our machine. What are they using? What does this code look like? How old is it? What's the structure? What kind of algorithms is it using? Those things, right? But there are whole communities that are missing from our user pool. And so this is why it's important for us to have your input, whether you're a user or not, to have your input in our user pool so that we can understand what your needs are. If you're going to tell me there's no way I'm ever going to use OpenCL, maybe I need to understand why, and understand how that's going to change the future. Or maybe you say, no, OpenCL is the way to go. I need to understand why. So part of my job is I serve on these two standard bodies committees. And I don't know what happened there. Hey there. I serve on these two standards bodies committees, and what I do is about 3 hours of my week, 3 to 4 depending on the week. I listen to compiler people talk about listen to compiler geeks talk about how hard it is to implement, and I tell them, you know, from a user's perspective, we really want this, and then I hear them go, there is no way that we could ever implement that. Or it'd be too hard, or and then they'll find edge cases immediately why this would not work all the time. And so I've learned a lot. Thank you so much, Michael, for all I've learned in the last year. But I am the voice of the user, and I'm the voice of the future user. And if you'd like to be a future user, I'd like to hear your voice. So I can come to them and say, please don't do that. That's too hard. Or no, you're focusing on the wrong thing. Because if I don't know what you guys need, then I can't tell the compiler people to stop digging that hole. So that's what I do over at OpenACC and OpenMP. Ultimately, our organization is agnostic when it comes to, we don't pick favorites, we don't pick architecture favorites. We pick what may be financially viable, what maybe we even think, you heard Jack earlier this morning, we had directives come up top that says we have to have diverse architecture. So there are different competing reasons why we choose the architectures that we choose. So tomorrow, it could change again, right? Something disruptive could come on the market and completely change. But I need to know what your requirements are. We need to know what your requirements are so we can continue to, say, mold these things so that it fits those future architectures. So that's what I do. I translate users' needs and I bring them use cases. And in the case of use cases, they might look something like this. We actually go down codes and users will tell us it didn't work this way because it didn't work because of this, or this is the reason. Right now in OpenACC, the conversation is on deep copy, so that translation is C++, right? These derived types, very deep data structures. How do you put that onto the accelerator? How far do you go into that tree? Those things came because of applications that literally users stood in front of us and said, it doesn't work, and here's what my data structure looks like, and here's how far I have to change it so that I can put it on the accelerator. So that's what I bring to OpenACC and OpenMP. So the future, for me, here's my future predictingness of a young lady who started on a 286. My future predicting powers say that I think the future is descriptive programming, where you're not telling it, this is how many iterations of the loop. You're telling us, here's where the loop, what it kind of looked like. The loop looks like this. These are the variables that you need to be careful with. And here are the data things that you should worry about and keep on the device. Things that describe to the compiler something about your program. And less about exactly telling the compiler how you like to do things. And those sort of cues that you give to the compiler go from having to write something that's very, very dumb, because compilers are dumb. I'm not saying you want to keep things dumb for the compiler, but I think those extra clues is really where this is going. I think that this is why, if I were to bet, I would bet on descriptive programming. I think this is where directives fit. I think OpenACC, I think, is a little bit ahead of the curve when it comes to that. OpenMP, still very locked down when it comes to loops, for example. You have to be very prescriptive on how you want to do your loops. And so I'm hoping that those two can have a conversation, a broader conversation, at what that might look like as far as directives. And the reason why is because, like I said, we're agnostic. Today we're running GPUs. What's the next architecture going to look like? Well, you know, it could come from above, it could come from the sides. We're not quite sure what the future holds for us. So we have to make sure that those applications that live for 5, 10, 15 years, 20 years can continue to run on our So there's a little bit of proof that there's already some influence that OpenACC has had on OpenMP on adoption of some of these key points that I've made. I'd like to see more, and I'd like to see a little more descriptive type directives make it into OpenMP. But already we're collaborating. In fact, a lot of the voices that I hear on the phone and the folks that I meet on both of these sides, they're on the same call the other time, you know, the other week, the other day of the week. So, you know, we're all working on the same problem. We're just trying to do it from different perspectives. As far as training, we hold lots of training, so it's open to the public, number one. We have webinars, we have remote training. Sometimes the training is broadcast. I bring in famous people like John Levesque to come and then teach. And we do hands-on. John Levesque did a hands-on OpenACC right in the beginning, just before 2.0, right? Just before we have released 2.0. We do a lecture style, and we also do hands-on style. In fact, the coolest thing that we're doing right now, I think it's pretty cool. We're hosting a hackathon next week. And this hackathon has been a lot of work. And I have 2 mentors here, so John Levesque is a mentor for one of the teams. There's 6 teams. I asked them to have 2 to 4 people each. And I'm getting close, right? 2 to 4 people each in each team. They've been working with these mentors now for the last 6 weeks, so thereabouts. Some more than others. Some jumped on it right away, and others took a little longer. And we chose a vast variety of applications. Some of them are users, some of them are not. We have a machine learning application, for example. We have another one that's a weather application. Well, what happened?
Is that a 286?
That's probably an Apple II. I remember doing that in middle school. It was an Apple II. It didn't come with an OS. I had to actually load it from a 5 1/4 floppy. So I feel a little old school. Just a little bit. The other cool thing about it is, so this is in response to what I hear a lot is something new comes along, and I'll do a training, and I'll talk to the users afterwards, or people that attended the training, and say, you know, were you able to use the things that you learned in the training event? And they tell me, well, you know, I started, but then I got stuck, or I didn't have enough people to do it, or, you know, work happens. And so this kind of is my attempt to solve all those things. You're going, you know, well, these teams are going to be sequestered for a week. They're going to be away from work. There's windows, don't worry. So we got a place with windows. There's going to be food flowing, fountains of coffee and caffeine, and they're going to be there hacking with, you know, their friends and then new friends that they're meeting, and hopefully they'll leave there OpenACC experts, because I got OpenACC experts like John Levesque, Jeff Larkin in the back. There's 12 mentors, 2 per team, and I'm trying to get above that initial sort of hump that gets people going, and then they can go off and they're experts, right? They know what they've seen it all, and people kind of push them over the little places where they normally get stuff. So those are the sort of innovative things I'm trying to do. In conclusion, there's no avoiding mini-core. I hope I convinced you of that. We think algorithms to expose more parallelism. Try not to get stuck too much with something that's been there for a long time. Maybe rethink it. Sometimes, you know, like in climate, it's not so easy to do. Directives are I think they're morphing into descriptive programming. I think that this is where it's going to go. This is my personal opinion, and I see more and more people talking about it. And I think this has kind of actually come out a little bit today, too. Memory placement is very important. Flops are free. I keep telling people, don't avoid flops, don't avoid calculations, avoid reads and writes. That's where your next, this is where I see a lot of people making mistakes. So avoid reads and writes, keep data local, flops are free, recalculate if you have to. These things can be calculated, no problem. Standards are built from application requirements. So if I don't see your applications, or we don't understand your application requirements, we can't bring that information to the standard committee. So let us know, even if you're not a user. I really like to know your experience with OpenMP, OpenACC, and how it's working for you. Training events are open to the public, so please look at our website for training events. You can attend remotely. Most of the things I do have remote, but if you'd like to come and visit and see Titan and take a picture next to Titan, that's my hobby. I like to go to supercomputers and take pictures. And also, we're looking for domain-specific communities. I'm looking for domain-specific communities that have a specific thing that they do, and whether that's geophysics or some specific little niche to do training on. Because I find that a lot of community-centric training, I think, helps to get them all together in the same room and helps them brainstorm and learn from each other and learn from what they've been doing. So that's where I'm at. I'd like to acknowledge people, and I'm not going to put the question slide because I don't want to hear from you.
Thank you, Sasha.
Thank you.
Thank you very much, Fernanda, for a very